Hi, this is Professor Jimenez. I will explain an application and how to design a micro sequencer. A basic micro sequencer, or the foundation of generating a sequence, is created by using a memory, which can be a 27F16, like a flash memory. And to scan a memory, you have to use a counter. This is a 4-bit binary counter, and this counter takes care of scanning the locations, the data that it is stored right here. In this case, the data is applied to a speech processor, but it can be applied to any other device. So when you want to read the data in a memory, you have to scan it in the lower bits, in this case A0 through A3, which is 2 bits, so you can scan up to 16 bytes. Okay, 16 bytes of memory. The memory is the data is given in this data bus from output 0 through output 5, because output 6 and 7, they are used for other purposes. In this case, output 6 is used to reset the counter, okay, and reset a flip-flop that it is right here, the reset of this 4520 counter, which is used as a single bit flip-flop. So, and why it is used as a reset? Because when you finish the data that you are delivering and you want to stop that, then on the 6-bit 06, you will write a logic 1, which will immediately reset the counters, and of course the counters will take some nanoseconds, in this case around 300 nanoseconds, to clear the memory, plus the propagation time, the delay that the memory requires to clear the data. So if you only scan this, and the latch is which controls address 4 and address 7, if the latch is equal to 0, so the counter will start scanning from location 0 through 16. If you want to scan another block of memory, you have to enter data here. So you enter number 11000. That will, and you store it with the latch clock here. So A4 will be 1, the rest address inputs will be 0. If A4 is 1, the binary weight of A4 is 16. So when this counter starts counting again, it'll scan memory locations from 16 up to 16 plus another 16 up to 31. So you when 42 on the latch, as I said before, it is 0, you can scan locations from 0 to 15. When A4 is 1, you can scan locations from 16 to 31. Now, if another case, if B2 is equal to 1 and A is equal to 0, now look at the binary weights. So A0 through A3 is 1, 2, 4, 8. This one is 16, 32, 64, 128. So if A5 is 1, you are in location 64. Okay, because as I said, 1, 2, 4, 8, and A4 is 16. So if A5 is 1, if B is 1, or A5, you have 32. So now you will be ready to scan locations from 32 plus 16, so 32 up to 48 or 47. So this is how you select the blocks of memory, and every block of memory will have 16 bytes of data. Okay, so we can think of these test inputs as the masking inputs, or as the locations that will indicate to the memory where to jump This way the memory will jump to those locations. In this case, there are 4 bits, so 16 different locations. Once the latch addresses one of those 16 different blocks of memory, the scanner will scan those bytes available. Sometimes, of course, you don't need the 16 bytes for every block of memory. So this is why you have the 06, which will restore, which will clear the counter, and once the counter is clear, it'll go back to the initial address where it is scanning. Okay, so this is the one basic way of addressing a memory with 16 blocks of memory, and with this counter acting as a program counter, because this one is addressing or scanning the memory, and this one is selecting the block memory. So the data is delivered, and so in this case the speech processor delivers every allophone, every sound, and the speed of those sounds depends on how the processor response. That way the standby and the ALD pins start creating a feedback, and that's why the clock starts scanning at different speeds depending on how the speech processor responds. This flip-flop acts as 4520 acts as a flip-flop where you enable this gate to start oscillating. Okay, and this is a circuit that enables that debounces the switch by generating a transient pulse, and then you get a clean low pulse, and when it goes high, it starts acting on the counter. So the flip-flop enables this sequence, and once everything is done for every sequence of data, 06 sends a pulse, resets the counter, and resets the flip-flop, this flip-flop. Okay, so this is how basic microsequencer works. Sometimes I include in my schematics, I include the timing diagram, but the timing diagram I will explain it in another lesson, in other types of lessons. Okay, thank you.